This video is going to focus on solution concentrations. We've already done a lot with this with the Beers Law Lab, so hopefully this should be a good review and kind of help to clarify anything that there was still confusion on from that lab. Molarity is typically the way we represent concentration. It's represented with a capital M, and that M tells us how many moles of the solute have been dissolved in a given volume in liters of the solution. Remember, there's two things that make up your solution, the solute and the solvent. Water is your universal solvent, and that's why the majority of your solutions that we're going to use are made with some sort of solute added to water. Standard solutions are ones whose concentrations are known pretty accurately. You guys are going to standardize a solution of NaOH in our next lab. And then dilutions are used to prepare solutions that we need concentrations of that either aren't as easy to obtain by making a standard solution, or ones that once we have a standard solution for that substance are relatively easy to make by just adding water to a certain amount of that standardized solution. And we can use the equation M1V1 equals M2V2 to help us determine how many milliliters of a stock solution we would need to make, or if we have a certain volume of a stock solution, what we could prepare of a dilution. These next two slides are going to look hopefully pretty familiar. They kind of go through the process we use to make our standard and dilution solutions in the Beers Law Lab, where you weighed out your solute, you added some water to it and got it to dissolve, and then you brought the water up to the calibration mark on your volumetric flask, and you capped it and inverted it, and that prepared your standardized solution. A dilution is prepared by taking a certain amount of a stock solution, either using a very precise graduated cylinder, which is what you all did, or you could use a volumetric or graduated pipette. You obtain some of that standard solution, you add it to water, depending on what you're working with. Sometimes you're going to go ahead and put some water in there, especially if it's like a strong acid or something like that. And then you're going to bring it up to the calibration mark and cap and invert to make your dilution. Hopefully you see in that last picture how the stock solution is definitely a little darker, more concentrated in color, because that bright yellow solution to the right has a lot of water that has been added to it, and that has decreased the intensity of the color. So we have 4 practice problems to work through. The first one and the second one actually are both going to be dealing with finding the concentrations of a solution, as well as the concentration of the ions being used to make up that solute. So we are given that there are 4 grams of NH4Cl, ammonium chloride, that's dissolved in enough water to make 500 milliliters of solution. We want to know what the concentration is of that NH4Cl, and then what are the concentration of the ions respectively. So when NH4Cl is added to water, it's going to split into its relative ions, the cation and the anion, which would make it split into NH4 plus and Cl minus. So those are all in a 1-to-1 ratio with one another. To find the molarity of that solution, which is what we're going to use to determine its concentration, we would divide its moles by the liters, the moles of the solute by the liters of the solution. We have an amount in grams, and we have an amount in milliliters. We can use the grams to help us get moles, and we can use the milliliters to help us get liters. So if we go with that molarity equation in mind, we would take the 4 grams of NH4Cl and divide it by 500.0 milliliters. I had an extra 0 in there, sorry. We can't just leave it in grams per milliliters. We have to convert the grams to moles, and we have to convert the milliliters to liters. So we need to use the molar mass of NH4Cl to get to moles, and then we need to use the fact that there are 1,000 milliliters for every liter to get the volume converted to the correct units. Our grams and our milliliters cancel out, and when we multiply and divide, we use the 4.00 to determine our sig fig, since it has the fewest, and you get 0.150. That was the concentration of NH4Cl, and because NH4 plus and Cl minus were in a 1-to-1 ratio with NH4Cl, that is their concentration as well. Our second example is going to look a lot like this, but we are going to be dealing with having more than one of the respective ions making up our solute. When K3PO4 dissociates, it makes 3 K plus ions and a PO4 minus 3 ion. What that tells me is that for every 1 mole of K3PO4 that is dissolved, I will make 3 moles of K plus ions. So that's something to keep in mind with its concentration. The ions for potassium are going to have a greater concentration than that of their solute because of the number of potassiums that were needed to make up that ionic compound. This time we're taking 1 gram of potassium phosphate and we're dissolving it in 250 milliliters of solution. We want to determine its concentration and the concentration of the ions. So we're going to use our molarity equation and we're going to take the grams of K3PO4 like we did in the previous example and divide it by the volume, 250.0 milliliters of solution. Now you could do these separately. You can do them all in one step. It makes no difference to me. But we need to get the grams into moles and we need to get the milliliters into liters. Again, sorry about the extra zero for the milliliters. I prefer just to do it in one step, so you're going to see me go ahead and cancel out the grams of K3PO4 with its moles using the molar mass, and then converting the milliliters to liters. The grams would cancel, the milliliters would cancel. The 1.00 determines my sig figs because it's the one measurement with the fewest. And so I get 0.0188 molar is the concentration of K3PO4. Now PO4 minus 3 is going to have the same concentration as the K3PO4 since they're in a 1-to-1 ratio with one another. But because K3PO4 is present 1 time compared to the 3K plus ions, we would have to triple it to get the potassium concentration. And we see that when we do that, the concentration shoots up to 0.0564 molar, while with phosphate again, 1-to-1 ratio, it gets to stay at 0.0188 molar. So the last two are very similar to the Beer's Law Lab. I'm telling you that we are going to prepare 0.5 molar solution of sulfuric acid. We're going to make a 1 liter solution of that. And we have an 18 molar concentrated, our stock solution of sulfuric acid to start with. So if we use M1V1 equals M2V2, we know what the concentration and volume are of one of our two solutions. We know the one for our dilution, and we know the concentration of our stock solution. I don't care which ones you make 1s and 2s, but you got to make sure that you pair the right volume with its concentration. The units for concentration do not have to be in liters, they just have to be consistent. The molarities cancel out. I divide both sides by 18, and that tells me that I would need 0.028 liters of that 18 molar solution to make my 1 liter. I can't really measure out 0.028 liters, so I go ahead and convert that to milliliters. And I would take 28 milliliters of 18 molar H2SO4, and I would add it into roughly half the amount of water that I need to prepare for my solution, get that stirred, and then bring it up to the final volume in your volumetric flask with water to 1 liter. And then our last one is going to be making more of a standardized solution. We're going to be doing it from the salt. We want to make 0.5 molar NaCl2 from its salt nickel 2 chloride hexahydrate. So to do this, we need to figure out how much of the salt we need to obtain, and that would be its mass. We can't get mass from molarity, but we can get moles. So we're going to find that part first, making the molarity and the liters combined together to give me moles. And then I'm going to use molar mass to get me from moles to grams. So when I multiply the molarity times the liters, the volume does have to be in the appropriate unit so that the liters will cancel out. And then I would multiply by the molar mass to get rid of the moles and to go to grams. Goodbye liters, goodbye moles. I had 2 sig figs in the 0.50 molar concentration, so I want 2 in my answer, which is 120. And I would take that amount of the nickel 2 chloride hexahydrate, and I would dissolve it again in roughly half the volume of water that you need to prepare your solution. Once you get that dissolved, bringing it up to the final volume in a volumetric flask with distilled water. So how I know whether I'm going to be preparing a solution where I need to find grams as opposed to milliliters is going to have a lot to do with, am I given 2 different solutions to work with? In this case I wasn't. I was given a volume and a concentration of the solution I wanted to make, and I was told I'm making it from the salt. Whereas with the previous problem, you were told you were making another solution, but you were told you were making it from a stock concentration. So I have to give you some clues so that you know whether you're finding it for a dilution or whether you're finding it to prepare a stock solution. And I will always make sure I do that.